good morning, or good afternoon, depending on what part of the country that you're in. My name is Tim Buttram. I work at Cascade Steel Rolling Mills. We're about 40 miles south of Portland, Oregon. And Chris has asked me to provide a little summary of how things are being done at our plant and how EasyPower is helping us get to where we want to be in our plant. So we'll get started. First off, we'll have some operating facts about our facility in McMinnville. We have a little over 400 people that are employed at Cascade Steel. We have actually two feeds that come into the plant. One is at 115 kV and the other one is at 230 kV. The 115 is for our plant power distribution and 230 is for our melting. Our main distribution voltage is 12,470. We also have 2,400, and of course we have a tremendous amount of 480. We circulate a little bit over 40,000 gallons of water per minute in the melt shop in the caster areas. We circulate anywhere between 12 and 15,000 gallons per minute of water for the rolling mill areas, and this is soon to increase probably to around 20,000 gallons per minute. Annually, we go through a little over 10 million pounds of alloying material as we're making steel. We consume over 600,000 tons of scrap annually. And we go through over more than 13 million pounds of lime every year. And here's some video that was shot in our plant, and what we're going to do is we're going to take a little tour through the process, and you can pretend that you're a piece of scrap and you're going through the process. And so we're going to start with the melting in the melt shop first, and we'll get started. And unfortunately, the sound is, you're not going to hear the sound on this webinar, but here you can see the roof swinging open on the EAF, and that's electric arc furnace. That's our melting vessel, and we're getting ready. You can see the scrap bucket coming in, and this is how we load the raw scrap into the electric arc furnace. The bottom of the scrap bucket is a clamshell design which opens up after the bucket's centered over the roof, and then the roof swings back in as the bucket is moving out. When the roof reaches home position, the roof will automatically center up, lower, and power will be turned on to the electrodes. And here you can see the electrodes coming down into the EAF, and now we've started arcing. And this is what we call bore-in, which is the most violent part of the heat. And again, this is about 50 to 52,000 amps to begin with, and by the end of the heat we'll ramp it up to probably somewhere around 62, 64,000 amps. Now you may wonder, okay, once the scrap is melted, how do we get it out of the furnace? Here you can see we've got a refractory line ladle positioned under the furnace, and once we get to somewhere between 2930 and 3000 degrees, we'll actually move the molten steel from the melting vessel into the ladle, and this is called tapping a heat. You can see the trough there on the right. That's how we add some of those alloys that you saw in the consumption numbers. Once the ladle is filled to desired capacity, the operator will hydraulically move the furnace backward in order to stop the flow of steel out of the tap hole, and we'll see that shortly. And here we can see that the ladle is getting very close to being at capacity, and there goes the furnace. This is called rocking it back, or back to slag position. And you can see that the flow of steel has stopped coming out of the furnace, and now they'll make preparations and start the next heat, and this ladle will be moving to the next refining process, which will be coming up in the next slide. This process is where we take the steel to the ladle metallurgy furnace, and we actually get the chemical and the heat to where it's needed in order to move to the next process, which is casting. And here we can see the ladle on the rail car or the tap car on its way to the LMF station. Now this steel is somewhere between 2930 and 3000 degrees. The steel will be at this processing station anywhere from 10 to as much as 30 minutes. And the LMF is very much like the EAF in that we use current conducting arms, we have three-phase AC, and really the major difference here is that the LMF, we're just adding heat, we're not melting scrap as you saw in the EAF. The next step in the process is casting, and here you can see the turret, and there's two ladles on the turret, and we go from the turret into a tundish, and from each tundish you can see the molten steel going in to water-cooled molds, and this is how we get from a liquid metal into a semi-finished billet form. We typically cast a 6x6 billet. Here is the runout area of the caster where the liquid has been formed into 6x6 billets, and at this station these billets will be cut to specific lengths for the next process in the rolling mill. You can see that a torch just made a cut on that billet, and all of these billets are independently, or all of these lines for each billet is independently operated. We have torches for each line, and we can run 5 strands at a time on the caster. Now that the steel has been cast into solid form, we're ready to move to the next process, which is rolling. And the first process is the billets will be reheated and brought back up to rolling temperature, and then will be put through the rolling process. And that's what you'll see in this short video. Here's the billet coming out of the reheat furnace, and the billets are typically somewhere in the neighborhood of 2000 to 2200 degrees. We have a 17 stand rolling mill that we take continuous reduction from one stand to the other to get the billet to a finished desired dimension. Now as the reduction gets more increases, the length of that billet increases. We make primarily 2 products, well, not just 2 products, but we make merchant bar and we make wire rod. And what we see here in this video is the wire rod. It's coming off of the rod block, and the first shot was coming off of the laying head. And we typically, in some of these products with the smaller wire, we will get in excess of 5,000 feet off of one billet. Here's a really good shot of the wire coming off of the laying head. And then from the laying head at the end of the conveyor, we form coils, wire coils on cars, and this is a good shot of how that wire is collected off of the laying head conveyor and formed onto these cars, that we can do a little bit more processing, we can do some compaction, inspection, and then they're tied and ready for shipment. And here's a coil that's just about finished coming off of the conveyor. Now these coils primarily are anywhere between 5,500 and 6,500 pounds each. We'll take a look in the next video, we'll take a look at the other side of the process, this is the wire side, we'll take a look at the at the rebar side of the plant. And here we can see rebar coming straight off of the rolling mill. This is the end of the 17 stand rolling mill. The rebar is cut to semi-finished length and is routed down and will go across a walking beam cooling bed, which you see here. As the rebar walks across the cooling bed, it cools off to a little bit more friendly workable temperature for more processing and ready to make it ready for shipment. We typically, off of one billet that's anywhere between 30 and 40 feet long, we'll get anywhere between 5 and 7 of the mother bars that you saw coming. Now this process, this is where we're getting the rebar to what the customer is going to receive. We're cutting the rebar to customer specific lengths, and then we'll sort the rebar into specific numbers of rebar per bundle for shipping. And of course the customer tells us how many bars that they want in a bundle. We can accommodate almost any request from customers. This next process is where these bundles are tied, and the tying machine actually has 4 of these tie heads, and the longer the bar, sometimes we'll have to make 2 or even 3 stops on an extremely long bar to do the tying. But as you can see, this tying machine is a very vital part in the finishing process, because these bars, as you see here at this stage in the process, are probably still around 500 to 600 degrees. The bar comes out and it's tied and it's ready for shipment. This is a single line of our 230 power feed into the plant. This is something that we are finding to have more and more value at our facility. That is something that EasyPower makes it very quick and easy for us to generate these single lines, and we are in the process of doing even more modification on these single lines to provide more information in very quick manner to our maintenance people and to our operations people. This is a power graph for EAF. The EAF is here on the left side and the LMF is on the right side. And we are doing something that I think is fairly unique. There are probably some other people that are doing this, but what we're doing is we're actually getting ready to use winding temperature as part of our electrode and power regulation in our furnace. The top graph, the red is megawatts and the blue is megavar, and in the bottom the red is winding temperature and the blue is oil temperature, and this is the EAF transformer, an 84 MVA unit, and on the left hand side it's the same information but for the LMF. These are some pictures of some of the equipment in various parts of our plant, and you can see that we are in the process of getting arc flash labels on this equipment. We've made, since these pictures were taken, we've made some more improvements in labeling. We've got additional hazard labels, but the ability that EasyPower gives us to make these labels and to do the incident energy calculation is really, really convenient in our plant and to our people. One of the programs that we have underway is replacement of old electromechanical relays, and we're going to more efficient and more smarter relays that we can get more information out of. And one of the big features that we like about these relays is that we have a maintenance mode and we have a normal mode that we program these relays for. And of course, one of the things that we really rely on EasyPower is the ability to know what our incident energy is in a particular location when we're in maintenance mode. And this is a really big deal for us because we do a lot of breaker interaction. We do a lot of switching. We have to rack breakers in and out of equipment quite often, especially on down days. And here is a picture that is from a particular piece of equipment in one of the rolling mills. And at first glance, you may think that, well, these labels are the same. But do you see any differences? The top label, as you can see down on the bottom, is when the relay that controls the upstream breaker is in normal mode, and the bottom is when the relay is in trip mode. And this is one of the examples where we really have a major impact on personnel safety, and it makes it easier for our maintenance people to do these activities because in a lot of cases we get the incident energy down to even to a number 2 PPE level, which for us a number 2 PPE level is less than 8 cals per centimeter squared. We kind of missed our target a little bit on this one because our maintenance personnel, they still have to wear more than typical level 2 PPE to do interaction with this equipment. But we think that going from 121 down to 9.7, we think that is very significant reduction in exposure to our people. And what we think is the best thing about this is that our people in our plant, they understand what these numbers mean, and they understand that we are making a push to improve safety in our plant. I'm sure that most of EasyPower users have seen these reports before, but this is something that is very, very convenient for me and for other people in our plant, but for me mainly because when we do install new relays or we have a change in our process, I can take this spreadsheet or this report, I can take this with me to the field, and when I'm programming the relays, I have this with me to make sure that I'm putting the right set points in the relays. And I think this is a very valuable, another very valuable tool that EasyPower provides to us, and this is one of the things that we use in the field very, very, very regularly. I included this label. This label is on a pretty unique piece of switchgear in our plant because we're actually bringing power from our local utility in as a backup to our normal power feed, and this is something that we don't do anywhere else in the plant, and because of that we use these red danger labels to warn people that there is something different and you need to know what the difference is before you start interacting with the equipment or doing a lockout, that there's more steps to this lockout. And the reason that I included this slide is because this diagram that you see in this label, this was taken directly out of EasyPower, which made this label very easy to create. And our people, our personnel, our maintenance personnel, they're really on board with this new signage that we're putting up, and I think it's making an impact in our plant. What are some of the things that EasyPower has allowed us to do at Cascade Steel? It's allowed us to identify underrated breakers that we have in service. It's helped us identify underrated switchgear that we have in service. When we do replace switchgear, we know exactly what parameters to specify for the new switchgear. We've identified areas where we're in excess of 40 cal, and we have procedures to deal with that. We can determine alternative methods to reduce arc flash hazard. The maintenance button on the relays is just one of the methods that we're using. And really the most important thing, in my opinion, is that we are creating a new awareness for electrical safety in our facility. And I think that that's really what our goal should be. I mean, having the labels and being in compliance, that's all well and great, and it's the things that we should do. But if we're changing the culture of our people in our facilities, that's where we really begin to see the fruits of our labor. And in recognition, this presentation and these pictures would not be possible without the efforts of the men and women at our facility in McMinnville. And special thanks to Mr. Jim Melton for his efforts and his help in doing some of these things that you're seeing. And Chris, I guess with that, I guess that we'll stay on for a couple of minutes and answer any questions or address questions as they come in.
That's right. So this pretty much concludes the webinar for today. And thank you again, Tim, very much. And have a phenomenal week. Thanks.
Thank you.